That ding means it's ready to learn. Nate, we spent about 3 days looking at distance versus time graphs. On a distance versus time graph, what does the slope tell you? Looking for a word that begins with, yeah? Velocity or speed. How fast, if you want to make a generic that kind of can apply to both. The height, the y-coordinate, told you how far, the distance. Today we're going to look at velocity time graphs. And we're going to ask ourselves, what does the slope tell us? I guess the height on a velocity time graph will be how fast. If the height on a distance versus time graph, the y-coordinate was how far, the height, the y-coordinate on a velocity time graph will be how fast. So, we're going to start off with a bit of review. Here's a graph. What kind of a graph is this? And Geo, from now on, every time you see a graph, you're going to have to, before you start plunging into the question, look at the y-axis and make sure you know what kind of a graph it is. Because now we're going to be looking at different types of graphs. And every year I have some kid who just assumes everything is a distance versus time and answers all the questions that way. And I read. So what kind of a graph is this? I see meters, position. Okay, this is a distance or position versus time graph. It says an object's motion is described by the following graph of position versus time. What's the object doing between 2 seconds and 4 seconds? So between 2 seconds, which is right there, and between 4 seconds, right there. What's it doing? Forward? Speeding up or slowing down, or constant speed? How can you tell constant speed? If it was speeding up or slowing down, what would you see? I'm looking for a word that begins with the letter C and rhymes with nerve. Yeah, it'd be curves, steeper or shallower. Okay, so let's say forward, constant speed, and in fact, then it asks, what's its velocity during that interval? You know what? Since that interval is a nice straight line, we don't need to get a ruler out and lay it down and do the instantaneous curve trick. I think we can just go rise over run of that little linear chunk. I know the overall graph is curved, but there's a nice little linear chunk. I think if I read across, I have a height of 54. I have a height of 18. I think the speed is going to be 54 take away 18 over 4 take away 2. I'm going to do that in my head. Brisa, 4 take away 2 in your head. Thank you. In fact, I'm going to do the top part in my head as well. 54 take away 18 is 44 take away 8. It's 36. It's 36 divided by 2. Double check me. Does that whole thing work out to 18? Yes? And that would be meters per second, because it's meters on the y-axis and seconds on the x. Okay. B asks, what's the object doing between 6 seconds, which is right there, and 7 seconds, which is right there? Ooh, he even used the physics word. Did you hear him? He said, it's at rest. Then it says, what's its velocity? So if I asked you for the velocity as a number, what would you say for at rest? 0.
For that, do we have to write the
meters per second? I probably won't be that fussy for a 0, but I almost always will. Not because I'm fussy on the units, but when I look at a 0, because the 0 is 0. I want the units so I know what the heck it was. Often when I glance at a number, even if you don't put the units, I can probably figure out where it came from because of how big it is. Not so much so with zeros. So I usually do. Hey, what's the object doing between 8 seconds and 10 seconds? So there's 8 seconds. There's 10 seconds. What would we say there? Going backwards? Backwards. Constant speed. And I can even tell you the speed. It's going to be negative. This one's a little trickier to read. Let's see. We're that high right there. This is a weird scale. What's each square worth? Well, you know what? Let's figure it out. Let's look down here. How many squares make up to 18? No need for a calculator yet.
4.
I think 3 squares. Don't count lines, count squares. How many squares make up 18? 3. So if 3 make up 18, what's 1 square worth? 6. So it's going to be 54 plus 6, 60 plus 6. I think right here, do you agree with me, is 66 high? I think, yes? And here is 6 more than 36. 42 high? So I would go 66, well, yeah, take away 42. Because I have the negative there already, I can go bigger minus smaller. If you wanted to get the negative to show up on your calculator, you would go 42 minus 66. But I got the negative already, Josh, so I'm going to be sloppy and go bigger minus smaller. Over 10, 8. Brisa, what's 10 take away 8? Same answer as before? Yeah, okay. Keep it up. And if I do that, I'll get negative 66 take away 42 is 26 take away 2, 24, 12? Is that right? By the way, looking for error checks, Eric, is this line steeper or shallower than this line? If you just eyeball it. So I'm looking for a number less than 18. Negative, I realize, but I figured the answer, the numerical value, it's going to be smaller than 18 because it's not as steep. So a bit of a built-in error check. If I'd gotten 24, I'd be nervous. Probably would have meant I forgot to divide by the 2, but I also would have been nervous. So what was the key idea? The slope of a distance or position or displacement versus time graph is the speed or velocity if they give me some kind of directional component. And Sarah, I've said if they don't give me a directional component, we'll keep it simple. This is what drove me crazy with the Science 10 thing last year. They go so focused on direction. Keep it simple. Positive, forwards, negative, backwards. Unless the question says different, that I can visualize. All right. Here's our key idea for today. What's the slope of a speed or velocity versus time graph? Pause the video. Got someone coming in late. So here's our key idea. What's the slope of a speed or velocity versus time graph? Let's see before Tato answers. Let's see if we can figure it out by looking at the units. Slope is what over what?
Rise over run.
So slope is rise over run. And I've told you a good trick if you're trying to figure out what a graph is to look at the units. What are the units on the rise on the y-axis? Meters per second. What are the units on the x-axis? So here's my question. What the heck is meters per second per second? In fact, we actually write it this way. Instead of writing it, don't write this down, don't write this down. Instead of writing it meters per second, since there's 2 S's on the bottom, we actually write it as meters per second squared. Does anybody remember what meters per second squared was? Tato. Acceleration. Hey! The slope is acceleration, which I'm going to abbreviate for the rest of the year as Excel, because I tend to abbreviate. What's on the y-axis, Matt? What letter? Speed. So here's what's happening. Right now you're going this fast. Later on you're going this fast, this height. Later on you're going this fast. Your height, your speed is increasing. You're accelerating. Positive slope, positive acceleration. You're speeding up. What would a horizontal... You know what? Let's see if we can figure all this out. Key idea. Oh, this one I put in a box for you. I must have been feeling really nice. The slope of a speed or velocity versus time graph is the acceleration. Ta-da! And you can memorize that, Catherine, if you want to, but I've given you a clever way to derive it. It's meters per second, or meters per second squared, which are our preferred units for acceleration. From now on, I said this earlier, but I'll repeat myself because you're teenagers. Whenever we see a graph, the first question we ask is, Make sure you ask what kind of a graph this is. Because the slopes and the heights, the y-coordinates, mean very different things depending on the type of graph, Josh. In fact, I think example 2 and example, here it is. Example 3 and example 4 are the same graph, but we're going to label them differently. The same shape, it's going to mean very different things depending on what kind of graph. But let's do example 2. An object's motion is described by the following graph of velocity versus time. Okay. Yep, I checked. It is velocity on the y-axis. So let's see if we can answer this. What's the object doing between 0 seconds and 2 seconds? Now, how fast you're going is not the slope. How fast you're going is the height, the y-coordinate. So, between 0 and 2 seconds, which I guess is that little chunk of line right there. Don't circle yours. I'll just do that so you can see what we're talking about. How high are we? How fast are we going? What's the y-coordinate? Zach? 6. Positive or negative? What would backwards look like on the, okay, backwards now is going to be down here below the x-axis. It's actually going to be a negative value. Okay? So we would say, what's the object doing? Forwards. Constant speed. And I can even tell you 2 meters per second. Oh, but it also wants the acceleration. It says, what's its velocity? Check. And its acceleration.
6 meters per second.
6. What did I say 2? Because I'm dumb. Tato candy for you. What's its acceleration?
0.
How do you know? Because what's the slope of that little chunk of line?
0.
And where is acceleration? Now, also, the very definition of constant speed means your acceleration is 0, but I can see it from the picture, too. Now you know why I put the units, just so that I know that that's the acceleration and not the velocity. We've got more than one number. What's the object doing between 2 seconds and 4 seconds?
Forward speed.
Speeding up forwards. Yes, absolutely. And then it says, please tell me the velocity. Oh, no, it doesn't ask for the velocity because the velocity is changing. All it can ask for is the acceleration. How can I find the acceleration? Where is the acceleration going to appear on a velocity versus time graph? Looking for a word that begins with the letter S and rhymes with Pope. So let's go rise over run. 12 high, 6 high, 6 over. This one's got a little nicer numbers. Between 4 seconds and 2 seconds. Brisa, what's the distance between 4 seconds and 2 seconds? Really? 2 again? You think I planned it this way for my latecomer? No, I would never do that. In your head, Brisa, 6 divided by 2? Every second, this guy is speeding up by 3 meters per second. 3 meters per second squared is you're accelerating at 3 meters per second per second. Every second, you're gaining 3 meters per second. What's the object doing between 6 seconds and 9 seconds? So there's 6 and there's 9. A lot of kids will say going backwards. Not. What's he doing? You're right, Jason. Slowing down. Still going forwards because we're above the x-axis, and on a velocity versus time graph, your height is your velocity. So still going forwards, slowing down. What's the acceleration? Positive or negative? So let's decide right now, what does a negative acceleration mean? It means that you're slowing down if you're going forwards. It means you're speeding up if you're going backwards. If you think about it. We'll talk about all that. But for now, it's going to be negative 12, 0, The rise is 12. Brisa, between 9 seconds and 6 seconds, what's the run? It's a trick question. It's not 2. 3. Negative 4 meters per second squared. Okay. Negative, or you could say slowing down. In other words, every second, this person is losing 4 meters per second of their speed. 4 meters per second per second. Example 3. Suppose this is a position versus time graph. Label the axis. So I'm going to go really lazy. D in meters. You can write the whole distance thing out, but we're just doing a rough sketch. What does the height, remember the height is the y coordinate, tell us? Maybe this is so obvious that it's tough. What does the height, the y coordinate, tell us? Yeah. Yep. I'll say the word distance, and I like your word, I'll put it in brackets. How far? What does the slope tell us? I didn't ask that, but what does the slope tell us? Speed. So what's the speed between time 0 and time 2?
0.
What's the speed between time 2 and time 5?
Negative 4 meters per second.
20, let's see. The rise is 20.
Oh, I lied. 5. That's 4 seconds.
The rise is 20.
Yeah.
What's 5 take away 2, Brisa?
Oh, yeah.
3. And while you're at it, you can look at Tato and just kind of shake your head in sympathy and say, I could do that in my head. I didn't bother making this one work out evenly. It's going to be negative, and I think you get 6.6 repeating. You know what? I'm going to go to 2 sig figs, negative 6.7 meters per second. What's the negative telling us? Going backwards. I guess we started 20 meters ahead from the start line. At rest, we sat there for 2 seconds, then we threw our car into reverse, and we're backing it back towards where we started from. So what's happening right at t equals 3 seconds? Backwards at constant speed, and I can even go more specific of 6.7 meters per second. I said backwards, so I didn't put the negative. Or you could have said constant speed at negative 6.7. Just don't go backwards negative, because backwards negative talking forward, right? Number 4, same graph, except instead of a distance versus time, let's make it a speed in meters per second versus time. Again, the first question we ask ourselves, what kind of a graph is this? It's important. So what's the height tell us now? Not how far. How fast? Fancy word, speed or velocity. Let's just say speed for now. Although you could argue if it's negative, it's telling you a velocity and there's a directional component, but whatever. So, what's the speed between 0 and 2 seconds? Here, the speed between 0 and 2 seconds was 0 meters per second because speed was the slope. What's the speed between 0 and 2 seconds here? It's both easier and harder because you're so used to looking for the slope, you're tempted to say at rest 0, but here the speed is the height, 20 meters per second. What's the acceleration between 0 and 2 seconds? Because where does acceleration show up on a velocity versus time graph? Slope. Fancy word we would then say is, hey, constant speed. What's the acceleration between 2 and 5 seconds? Well, I think negative. Yes? I think it's going to be negative 6.7. It's going to be 20 over 3. 3, I say, 3. And the units would be meters per second, or meters per second squared. So, on this graph, what's happening right at time equals 3 seconds?
Going forward, slowing down.
When are we at rest?
0, 5 seconds. Well, 5 seconds.
Yeah,
0.
t equals 5 seconds. Okay. All right. I like example 5. I like example 5. I like example 5. Example 5 is a nice question. Why would I say that? Did you hear me say it's going to be on the test? You're the kind of student that notices when your teacher emphasizes certain things? Okay. This idea of giving you one type of a graph and then asking you to sketch the other graph, I like. Probably on your test, I might make it just a sketch. Anyways, so we have a position versus time graph on the left, a velocity versus time graph on the right, and it says sketch the velocity versus time for this object here. Okay, let's go, we'll do each little interval, each little 5-second interval. Here, what's happening? What can you tell me about the velocity here?
Going forward.
More specific, as a number. How can I find the velocity? Where does it show up on a position versus time graph? Look at slope. So let's go rise over run. How high? Right there is 35. How high? So I'll write my calculations right underneath here. 35 take away 10. The rise is 25. Yes? What's the run?
5 seconds.
In fact, I think it's going to be 5 seconds is going to be the run for each little chunk. Brisa, in your head, 25 divided by 5. Okay. So how fast are we going between 0 and 5 seconds? 5 meters per second. How am I going to graph that? I guess halfway to 10, which is going to be, hanging in midair, like right there. But you can freehand that. You don't need a ruler. I guess each square on my velocity time graph vertically is worth 2. 2, 4, 6, 8, 10. So, all right. What's happening between 5 and 10 seconds?
At rest.
Oh, let's use green, Mr. Duick, since I've kind of gone with green. So that would be at rest, a line 0 high. Yeah.
Wouldn't that be impossible? Because you have to.
We're in our because you guys right now can't handle curves, I have to give you nice straight jagged lines. In real life, as I said before, objects don't move like this. In real life, objects would move much more like this. Curvy. And it would give us some stuff going on in there, calculus. But yes, great point. How fast? How high? 50. How high? 35. 50. 35. 15 over 5. Brisa, that's your cue. 3. So 3 meters per second is going to show up as the height here. And I guess that would be halfway between 2 and 4, yes? How fast? What's the slope? Positive or negative?
Negative.
50 is, no. Yeah, is the rise is 50, yes?
Yeah.
And the run is still 5? Knock, knock. Sorry? I disagree. Ah, negative 10. So that's going to be way down there. Negative 10. That weird kind of staircasey function on the right, yes, I totally agree, Tato. This is in our magic physics world where I have to give you nice questions because we can't handle curves all that well, but that would be the velocity time graph of that distance time graph, both of which are showing objects that don't move really that way in real life. I agree. Over what intervals are we at a constant speed?
0 to 5, 10 to 15 to 20.
Each 5-second interval. And you're right, Tato, the problem is our changes in speed are instantaneous. There should be curves. Over what intervals are we at rest? T equals 5 to t equals 10. Now, you could argue that constant speed, someone could say, Mr. Dewick, is 0 a constant speed? And we can get into a long discussion. And I would argue, yeah, it is. You're not accelerating. My definition of constant speed is you're not accelerating. And if you're at rest, you're definitely not accelerating. So far, so good. You guys are blazing. Okay. I like example 6. I like example 6. I like example 6. Example 6 is a nice question. It says, on the graphs below, draw 2 lines or curves to represent the given verbal descriptions and label the lines or curves as A or B. So we'll do 2 lines or curves here, 2 lines or curves here, 2 lines or curves here, 2 lines or curves here. We'll label them A and B. What kind of graphs are all of these? I think they're all velocity versus time graphs, but I always want to make sure I double check. All right. Moving at a constant speed in a negative direction or backwards. What would that look like?
Downwards a little down. Below 0, negative.
Don't write this down. Like that? No?
0.
Oh, from 0? Don't write this down. Like that? Is that a constant speed?
Oh, straight line below 0.
All lines are straight, Captain Obvious.
I mean, horizontal.
You know I'm ready for that. I'm queued up for that punchline, right? Zach, you're shaking your head. What would a constant speed look like on a velocity time graph? Yeah, I got that below. Ah, A would look like that. You can freehand it. You don't need a ruler. Try and draw a nice horizontal line. B says, moving at a constant speed in a positive direction. I'm going to add one more thing. Slower than A. How would I show slower than A? Not as high up, as A is low down. Constant speed, horizontal line. I'll do it in red. So, there. I'm going to do the right-hand one a bit later. I'm going to go down. Moving in a positive direction, forwards, speeding up. Would that work? Doesn't have to be a curve. Is not the speed increasing? Yes? Moving in a negative direction and speeding up in the negative direction. Moving in the negative direction and speeding up. What would that look like? Yeah. That. You're accelerating backwards. If you're going backwards and you're accelerating backwards, you're going to speed up. This would be car in reverse, stepping on the gas. Let's go back and do this one up here now. Moving with a positive velocity and a negative acceleration. when I say acceleration on a velocity versus time graph, what am I really talking about? I'm looking for a word that begins with the letter S and rhymes with Pope. So positive velocity and negative acceleration, I think positive velocity and negative slope. I think the only thing would be something like that, yeah? Positive velocity, we're above the x-axis. Negative slope. Let's call that line A. What about a positive velocity and a positive acceleration? Yeah? All right. You know what? I think I could have zoomed in. That's what I should have done to begin with. And that way in the back row you guys can see a bit better. Positive direction, slowing down. You saying? Okay. Negative direction, backwards, and slowing down. Because if you're slowing down, what speed will you eventually hit if you're slowing down, slowing down, slowing down? Well, first of all, 0, and so slowing down, I should have a line that looks like it's going to eventually hit a height of 0, the x-axis. By the way, I think I went on my rant about how in physics graphs mean something. Your x-intercept on a velocity versus time graph, that's stopped. That means something. That's when you came to a stop. Moving with a negative velocity backwards and a negative acceleration. Negative velocity and negative, wait a minute, instead of acceleration, what does acceleration mean on a velocity versus time graph? I'm looking for a word that begins with the letter S and rhymes with Pope. Negative velocity and negative slope. See, negative slope, right away I'm thinking it's going to be downhill. Yes? Negative, oh, so it's going to be a negative velocity below the x-axis and downhill. Got to be that, yeah? It's the only thing that satisfies that. What about a negative velocity and a positive acceleration? Whoop. Moving in a positive direction. First fast, then slow. Don't write this down like that. What would fast in a positive direction show up as? Like right there, maybe? What would slow show up as?
Negative acceleration.
Not as high. You know what? I think that works, doesn't it? Isn't that moving in a positive direction, first going really fast, then slowing down? No curve necessary yet. By the way, if you haven't figured out, all of these are different ways to phrase very similar things in the English language for the physics. Moving in a negative direction, first fast, then slow. I think. All right. Example 7 asks, which object has a greater acceleration? Stop. What kind of a graph is this? I better read. Oh, speed versus time. Because if it was distance versus time, where does acceleration show up on that? Not directly. You got to do some thinking. But speed versus time. Okay. Which object has a greater acceleration, the dotted line or the solid line?
Solid line. Or dotted line.
I've heard both answers. The good news is one of you is right. Because when I say acceleration on a velocity or speed versus time graph, what am I really talking about? I'm looking for a word that begins with the letter S and rhymes with Pope. Steeper slope, bigger acceleration. All right. Wow, we have A, B, C, D, and E. Okay. Before I even read the question, I glanced, are all five what are the five graphs measuring? What are we looking at? Okay, first of all, I made sure they didn't pull a fast one and sneak some velocity and some distance graphs. That'd be mean. I don't think I'll do that, but okay. A man starts at the origin, walks back slowly and steadily for 6 seconds. Then he stands still for 6 seconds, then walks forward steadily about twice as fast for 6 seconds. Which graph best depicts that scenario? A man starts at the origin, walks backwards slowly and steadily for 6 seconds. Then he stands still for 6 seconds, walks forward steadily about twice as fast for 6 seconds. Jason can't contain himself. He blurts out, what was that? D? How does that work? Isn't he supposed to start at the origin? Shouldn't it start at 0, 0? Or should it? If it was a distance versus time graph, we would start at 0, 0. Uh-oh. Jason, keep going. Give me your argument, Jason. So, what are you saying is happening right here?
I'm saying that he's walking slowly, steadily for 6 seconds.
Forwards or backwards, and how do you know?
Backwards.
Why?
And negative.
This is a velocity time graph. We're below the x-axis. Steadily, no slope. Steadily, acceleration is 0. Then what does it say?
He stands still.
Okay, and again, I totally agree with you, Tato. This part and this part are the unrealistic parts that I'm stuck with because I can't do curves with you because you don't have the math skills to handle it properly. I agree. So he stands still for 6 seconds, a velocity of 0, height of 0. Then what?
Then he walks forward.
Forward, so I'm above the x-axis. Keep going, keep reading.
About twice as fast for 6 seconds.
So this distance here should be about twice as big as that distance. It looks about right. Connor, has Jason convinced you that D is the correct answer? Say yes.
Yes.
I know it's a little awkward letting Jason be right, but once in a while, it's got to happen. All right, here's our next question, B. Supposing instead of all of these being velocity versus time graphs, supposing they were all distance versus time graphs, which would match that situation the best? So instead of velocity versus time, supposing they were distance versus time. Oh, I even found the graphic to show that. Cool. So what's the best position versus time graph here? Tato, convince me.
Starts at 0.
Okay, so starts at the origin, that gets rid of that one. Okay?
So he walks backwards for 6 seconds.
Backwards, where would backwards show up on a distance versus time graph? Negative slope. That gets rid of that one, that gets rid of that one. Right? Okay, so now we already got it. By the way, we've turned it into a true-false guessing question now, 50-50 odds, even if Tato's wrong. Keep going.
He's at rest, it isn't moving.
So here is the at rest section, a slope of 0, although there is a slope of 0 right there.
Moves like forward. Comes back up to 0. So it can't be.
And it does say that he,
He's at rest.
okay. Okay. So I think I agree with you. I think B. My issue here is somehow magically he starts out like a certain distance away and then magically teleports himself back to the starting line. Because on this graph, your height is your location, your distance. Is that all right? Good gosh, am I going to get through the whole lesson today? I just might with you guys. You guys are doing great. Okay. Remember when I said I like this question? I like it. Really what I meant was I like example 9, I like example 9, I like example 9. This is the kind of question you'll see in the future. Doing graphics for something like this is such a pain, it takes a long time. But sketches, that I can do really easily. So, sketch the corresponding graph. We're going to do a graph A and a graph B. What kind of a graph are we doing right here? Okay, what would graph A look like as a velocity versus time graph? Horizontal line? Above or below the x-axis? Way above or just a little bit above?
Just a little bit.
Oh, good. So there's line A, constant speed. Line B, are we going faster or slower than line A? And how do you know? Because the slope is B. I would take, if your line A was a bit lower or a bit higher, all I'd be looking for if I gave you this question, Alec, is do you have two horizontal lines and is B above A? So scale here, we don't care. I lied. We can handle curves if we're clever. What's happening in B in that distance versus time graph? Zach. I have no idea what you're saying. Your lips are moving, though. A little louder.
It's getting faster.
Speeding up?
Yeah, speeding up.
Okay. First of all, positive or negative velocity? Okay, so I'm not drawing below the x-axis. And speeding up? How would I show that? Speeding up. Again, if you drew your line, Zach, like that, I'd give you full credit because we don't have the ability or the math skills to actually say how fast it's speeding up, what the acceleration is. Or if you drew your line, like I'd give you full credit, but definitely a velocity that's increasing. Ooh. What's the distance versus time graph that would go with that?
Curve starting from 0. Yeah.
Positive or negative velocity?
Negative.
I'm going to ask you the same question. I'm just going to phrase it differently. Positive or negative slope?
Negative.
Same answer. So I'm already thinking it's going to be a negative slope. Don't be drawing something that goes uphill. Yes? Constant velocity or changing velocity?
Changing.
Changing. So constant slope or changing slope? Curve. Getting steeper or getting shallower? Getting bigger or getting smaller?
Bigger.
Faster and faster. Negative slope, getting steeper. Yeah? I think that works. Which in hindsight, now that I look at my answer for B, oh yeah, this graph here got flipped, this graph here got flipped. That kind of makes a nice symmetrical sense too. Cool. I didn't think I'd get through this whole thing today with you guys, but I think I will. I might even give you some chance to work on the homework. Describe the motion depicted on this position graph and then fill in the missing graphs. Assume the acceleration, if it's present, is constant. This class goes till 9:35. Okay, you know what I'm going to do? I'm going to make an executive decision. I'm going to continue this when I see you folks on Monday, but I'm going to give you 15 minutes to start some of the homework because you can already get a lot of these done. So if you want to start the homework, and I'm going to assign every question, so start the homework. However, if you don't finish it in class, and I don't think you will because I threw a whole bunch at you, on Monday we're going to finish off the lesson. I'm going to give you a take-home quiz on graphs, except that take-home quiz is going to include some velocity time graphs as well as some distance versus time graphs. And you'll also get some time to finish the homework on Monday. Is that all right? Because I'm kind of losing you guys here too. Geo's drooling a little bit, getting a little old. Okay?